From pairs we build a world of thought, of functions rule a path we sought. Equivalents for grouping, orders for ranking, each elements find its spot. Relations link the mind to heart, a logical and elegant art.
Whether we admit it or not, we human beings constantly encounter binary relations with one another in daily life. Professor and student, driver and passenger, landlord and tenant, to name but a few. In mathematics, we also want to describe relations in order to capture interesting phenomena. For that purpose, we need a proper definition for a binary relation, which should be both adaptive to various scenarios and rigorous for analysis. Here is its definition. Let A and B be two sets. A binary relation R from A to B is simply a subset of the Cartesian product A cross B. We call A the domain of the relation and B the codomain. Consider an ordered pair XY, where X belongs to A and Y belongs to B. If this ordered pair belongs to this subset R, we write XRY and say that X is R related to Y. If A and B are distinct sets, we call such a binary relation heterogeneous. If A and B are the same set, then the relation is called homogeneous. We illustrate this definition via some examples. For arbitrary sets A and B, the empty set is always a subset of A cross B. We call this the trivial relation. On the other extreme, the whole product A cross B is also a subset of itself. Every possible pair is included in this relation, which we call the universal relation. While these relations indeed fit in the definition, they are not particularly interesting, as such does not reflect any extra information about set A and set B. Let us turn to a geographic application. Let A be the set of cities and B be the set of countries. We can define a homogeneous relation, namely R1, from A to itself, such that a city X is R1 related to a city Y if X is a friendly twin city of Y. For instance, Beijing is a friendly twin city of New York, so the pair Beijing-New York belongs to R1. We can also define an inhomogeneous relation R2 from A to B, where the pair XY belongs to R2 if X is the capital of Y. For example, the pair Beijing, China, belongs to R2. On the other hand, the pair New York, United States does not belong to R2, since New York is not the US capital. In the rest of this section, we will consider the set of integers z and discuss examples of binary relations from z to itself. Consider the binary relation R consisting of three elements: 0, 1, 1, 3, 3, 6. There is neither evident pattern nor specific motivation here, but it is still a valid binary relation, since R is a subset of Z cross Z. This type of relations, due to lack of specific properties, is not of great interest to us. Next, define a relation R as follows. An integer x is related to an integer y, if and only if y equals x squared. For example, the pair 1, 1 belongs to R, since 1 squared equals 1. But the pair 2, 3 does not belong to R, since 3 is not equal to 2 squared. Notice that for each pair x, y in this relation, y is given explicitly as a formula in terms of x. This suggests that the concept of functions that we have learnt in high school can be regarded as special kinds of relations. To see another application, define a relation R such that an integer x is R related to an integer y if and only if 4 divides x minus y. For example, 5, 1 belongs to R since 5 minus 1 equals 4, which is divisible by 4. However, 7, 2 is not in R, since 7 minus 2 equals 5, which is not divisible by 4. To see why this binary relation is useful, consider an arbitrary integer x. The remainder of x divided by 4 is either 0, or 1, or 2, or 3. Based on such, we can regroup the integers into 4 distinct classes depending on their remainder, modulo 4. Hence, it provides an approach of classification. Last but not least, consider a relation R, where an integer x is R related to an integer y, if and only if x minus y is greater than or equal to 0. For example, 2, 1 is in R since 2 minus 1 is equal to 1, which is greater than or equal to 0, while 3, 5 is not in R as 3 minus 5 equals minus 2, which is less than 0. This binary relation captures the order of integers. Recall that take any non-empty finite subset of Z, there's always a greatest number in it. But the concept of being greatest is based on the order relation. Clearly, to discuss being greatest, we first need a way to compare two given integers and determine which is greater. That is precisely how the order serves us. We have seen that, although a binary relation can be defined arbitrarily in principle, certain binary relations are more useful, as they can be used to define functions, construct classifications, and introduce orders. What properties make these relations special? We will explore them in the sections to come.
Shinla Tensei